Okay, so let me propose a scenario to you. You've got your IoT deployment. Maybe you have a bunch of devices out there, a bunch of base stations connected over wires. And one of your base stations is out there. Maybe it's like a mile away. You got a wire going out there, and you can't communicate with it anymore. And you're wondering what's going on. Did something go wrong with the cable? Maybe a cable got damaged or cut or something like that. What would you do? How would you figure out what happened? So what you can do is you can drive out, look at the base station, it looks fine, look at your connection, it looks fine. Something wrong with the cable. Well, what are you going to do? Are you going to kind of like walk along every inch of that cable for the whole mile and kind of look and see where it's broken? That would take forever. When you need to troubleshoot a problem in the wide area, whether it's wireless or wired, you're kind of faced with this problem of you can't really physically inspect all your cables. And so this is a big challenge if you need to troubleshoot something. Well, it turns out there's this really neat trick you can do that's used by professional network engineers. And it's used to locate anomalies using something like kind of like a radar. And it's used for wireless deployments, it's used for wired deployments. It's kind of like a radar that you can kind of shoot down wires and kind of figure out if anything's messing with your signal in that wire. And this technique is called time domain reflectometry, or TDR. And I'm going to talk about this because this is a very useful technique for when you're deploying in realistic environments. So the idea behind TDR is it is a tool that can detect and localize variations in a cable or in a wireless deployment. It can detect things like deformations and cuts, splice taps if someone's tapping into your cable. It can detect crushed cable, termination points, sloppy installations, and so on. Anything that changes the impedance of the wire. What's really neat is it can actually tell you the difference between these things. It can tell you if your cable got deformed or if it got cut, and so on. So the main idea behind TDR is we're going to send a pulse down the wire and measure reflections. And we're going to measure things like the delay of the reflection, because the delay of the reflection localizes the location of the anomaly. But we're also going to look at the structure of the reflection, how the reflection comes back, because that gives us information about the type of anomaly. Okay, so to motivate this, I'm going to show you a video. So what we did here is I went online and I bought a big Slinky, a really big one. And what we did is we took the Slinky outside and we had one person kind of be at one end of the sidewalk and the other person be at the other end of the sidewalk. And then what one person is doing is they took the Slinky and they kind of shook it and sent a pulse down the Slinky. They send a wave down that Slinky. And you can see that when they do that with their hand, the pulse kind of goes down that Slinky. It kind of goes down and goes down. But something very interesting happens when that pulse hits the other end. When the pulse hits the other end, it gets reflected back. And it doesn't just get reflected back, it gets inverted. So someone sent a pulse on the right side, and then the reflection comes back on the left side. So why does that happen? Why does the pulse come back reflected? You'll also notice that the shape of the pulse changes. It gets more square. You'll also notice that the amplitude of the pulse decreases. There's some reasons for this. There's actually a lot of information about what's going on the other side of the Slinky from this pulse. The pulse is going out and it's hitting something, and we can tell a lot about how the other person is holding that Slinky by how it gets reflected back. In particular, the person on the other side is holding the Slinky fixed. If they had their hand loose and the Slinky kind of moved, the Slinky pulse would not get inverted. The pulse would come back and it would be non-inverted. So this is something that's really interesting. And it applies to Slinkies, but the really weird thing is this applies to wires as well. If you send an electrical pulse down a wire, you can send a pulse down, and if it hits a cut, or if it hits moisture, if it hits anything, it'll get reflected back. And the way it gets reflected back tells you a lot about what it's hitting there and where it's hitting that. And this is such a useful technique to diagnose what's going on. It works for electrical wires. It also happens to work for optical cable. It also happens to work for wireless signals as well. It's amazing how well this works. So let's kind of study this in a little bit more detail. If you have a Slinky or you have some sort of pulse on a string, and you kind of send the pulse down the string, the way the pulse gets reflected back tells you about the termination on the other side of the string. And I'm just going to tell you, and you can think about this. If you think about this, it's intuitive and it kind of makes sense, that if you have a string or a slinky or something like that, and you kind of send a pulse down it, and no one's holding the other side, it'll be just like this animation here. The pulse will kind of go down, and it'll just disappear. Nothing will get reflected back. So if you have no termination, your wave pulse will not be reflected at all. Now, if you have a termination on the other side, and that termination is loose, it's soft, someone's holding the slinky and it's kind of loose, or if something is able to move up and down a pole or things like that, you will get a reflection. But a reflection from a soft boundary is not inverted. You'll get the same pulse back. On the other hand, if you have a reflection from a hard boundary, your boundary is fixed and it's hard, your reflection will go down the wire, the string, and it'll get inverted when it comes back. On the other hand, suppose you have a rope or a string where you have kind of a thin string and it's connected to a dense string. What will happen there is some of your pulse will go through and some of it will get reflected. If you go from something where you're going from high speed to low speed, or a thin rope to a thick rope, your pulse reflected back will be inverted and it'll be reduced in size. If, on the other hand, you go from a thick string to a thin string, your pulse will get reflected back and it won't invert. And so what you can do is tonight, when you go to sleep, right before you go to sleep, pull up this slide and kind of reflect on this a little bit and think about it. Imagine yourself kind of taking a string and kind of doing this. And all these things will kind of make sense, because we kind of know how strings work and things like that. If you think about it, all these things are true. So the weird thing is, these things are true for electricity too. If we take electricity and we send it down a wire, or we take light and send it down an optical cable, or wireless and we send it through the air, we can learn about impedance changes and changes in propagation and things like that. For example, if you have a cable and the cable's melted, what happens is the cable's impedance changes. Not as much electricity can get through that chunk of the cable. So this is similar to a hard boundary. You're hitting something that's kind of like a hard boundary. Electricity is trying to get in and then not as much can get in, so some of it gets reflected back, and it's going to be inverted. Because when you hit a hard boundary, it's inverted. So what I have over here on the right is the output from an oscilloscope measurement of a melted cable, a real melted cable. And so what we did here is we sent a pulse down the wire. That's the initial pulse shown on the left. And what gets reflected back is shown on the right. And you can see the pulse gets sent down and some pulse gets reflected back, and what gets reflected back is smaller and it's inverted. So this is a big hint that if you see this in a cable, if you're kind of sending these pulses down, you're getting these reflections back, that you have some melted cable. On the other hand, if you have a cut cable, things look totally different. Here, we have a cut cable, you send a pulse down, and your reflection comes back, it's reduced in size, but it's not inverted. Because here we have an open boundary. There's nothing holding down the electricity. The electricity kind of hits this cut cable, and it gets reflected back. So it's an open boundary that can kind of move. Another example is moisture in the cable. Moisture is a little bit different, because moisture kind of gets around the cable in different locations. It kind of does different things to the cable. It kind of improves the ability for electricity to go through the cable in some locations. It reduces it in some locations. And so you see that in the TDR map, which I'm showing you down here. We have some water-soaked cable. And you see the initial pulse kind of goes down, and some of it goes through, and some of it gets reflected back. And you see kind of like a little bit more of a mess here. This is a signature of cable moisture. If you're doing TDR and you see this signature, you probably have water in your cable. If you have a faulty amplifier. So you have a wire deployed, you have something kind of amplifying your signal, and it's getting faulty, you're going to see a signature like this, where you're going to see some of your reflection come back positive, some of it negative. If you have a wire tap, it's going to look like this. You're going to see a impedance change, just a little bit of an impedance change as it kind of hits that tap. So this is really amazing if you think about it, that all of these different situations, the signatures just show up so well. TDR is a really powerful technique for you to figure out what's going on in your cable when you're doing real deployments. You can't go out and inspect everything. So in the future, when you do real deployments, you can use TDR yourself to figure out what's going on.